Welcome to Bio-Inspired Robotics Lab. It's located in engineering department, which is the heart of University of Cambridge. So currently, like a lot of things is going on here, like May Week, May balls and all. And we are excited to present our excited work in bio-inspired robotics. Why do we do bio-inspired robotics? Because biological organisms are very efficient. The bird eating a little amount of food can fly dozens of kilometers, and we walk quite a long distance, like eating a limited amount of food, and everything is polished and evolved in a long period of time and nearly perfect. So we want to capture those perfect characteristics and use it for robotics. So one of the examples that I want to show you now is the what we inspired from the robotic nose or robotic trunk, the elephant trunk. Elephant is like incredible animal that can do a lot of things using only one one trunk. Like for example, it can suck the object, it can pinch the object, and it can squeeze the object, and everything is like just only by this like small nose. So this gripper exactly follows those characteristics. It can pinch the object, it can suck the object, and yeah, it has two units of suction. The smaller one for the small objects like berries, and the bigger one like fruits for the fruits, and so on. Another important characteristic is that bioorganisms are very good in survival, so they can heal, self-heal. When we get a cut, we recover quite quickly, and other animals also recover quite quickly. That's why like there is like another way of research, of bio-inspired research, is like self-healing robotics. So these like two materials are one of those examples that can self-heal. Suppose that we use this finger for a gripper and get when it gets damaged, after giving it a bit of time, it can recover itself from the damage, and perform like nearly perfect recover to nearly perfect characteristics. We do a lot of work with the human-inspired systems. Like for example, our hands are so efficient that we can do like many fine manipulations. So we want to capture those like passive and characteristics that help us to do those tasks and build sophisticated robots. Also, we work on the like medical domain. We are trying to capture those features that the doctor feels during the inspection and palpation of the human body, like of the patient, and we are trying to replicate it, and so it can be used for the remote treatment or for the education in education purposes. So the other examples will be provided by Fan Yi, which will speak to you now.
So, okay. Hi. There is a demonstration of the robot hand that we are making. A normal robot hand is rigid and has a lot of sections. There are actuators between the sections. So the actuators make it move and grasp the object. However, in our project, our soft robotic hand is soft and passive, which means it has no actuator inside the hand. But it still picks up the ball successfully. Why does this happen? Because this soft robot hand is inspired by a natural discovery that animals' behavior not only results from their brains, but also results from their body, the interaction between their body and the environment. So we build a passive robot hand, and it still successfully pick up the ball because of its stiffness. But here is another question: that how does the robot hand know where the ball is and whether it pick up the ball successful or not? Inspired by human tactile, we built some sensors on the surface of the robot hand. Indeed, these sensors are soft and these are airbags. When the airbags contact the object, the pressure in the airbag change, and the robot will know the pressure change and understand whether it pick up the ball successfully or not, and then improve its success rate by changing its stiffness of the hand. Okay, let's pass the turn to the OHMC.
Okay, I'll jump in just before that. So we've seen some examples there of why we might use soft materials and soft sensors. And soft sensors we really like because they're much more similar to what we have in our bodies. We have soft tactile sensors all over us, and we see that in nature as well. And it's much better to get a rich amount of information that we can use. But they're much harder to get the data from than something like a traditional rigid sensor. In this case, this is temperature and humidity, and I can measure both of them just by reading out specific channels from here and knowing the temperature and the humidity on this sensor. But if we take some kind of soft material, this is a soft inflatable finger with sensors along the bottom to tell us how it's deforming, it's much trickier to work out what that means. This might not just be bending, this finger might be twisting, it might be stretching, and just from the information coming from the embedded sensors, we need to work out what that is. And there are different ways we can approach this problem. We can look at the data leading up to how it's deformed. So we might look at something, say, that's a twist. We know it's twisted to get to this state, so it's twisted now. Or we might use a big amount of data that we've collected already. And that's what's going on here. We've got a sensing skin, a membrane acting as a drum skin down here. It's made of a gelatin-based hydrogel, and it can record as we press it, but to get a big database of how it reacts, we're currently pressing it thousands and thousands of times in known locations, measuring the response, and then using that to build up later when the robot's not here, so that we can know how it's pressing, how it's being deformed. Like I say, this is made of a hydrogel material, as is this finger, which is biodegradable, which is edible, and which we can build really easily up in our fabrication lab. So I'm going to hand back to Arsen upstairs to show us how that's done.
Yeah, thank you very much, David. It was like a really insightful discussion about the sensing. And basically, those things that David discussed to you right now, like we do it here in the fabrication area. Basically, there are several ways to fabricate the thing. Like the first way is like printed using like 3D printer. Like current materials can be like really flexible, and we can print like, and we can basically prototype like very fast. This is like the first way of fabricate soft bodies. Another way is like casting. Castings are like, for example, we can use like some silicone or other rubber type materials and make the soft body out of it. So basically in casting, we make a mold, which is usually also 3D printed, and we can pour our material and make this, like, for example, like a rubber-like silicone structure. But in most cases, we have to embed like bone-like structure in it, and we have to embed the sensors in it, and it's like a more complicated. And we basically use both technologies, like, for example, 3D print the bones and then embed them into the flesh, like fabricated from the silicone. Yeah, about the sensor, like we can put like many kinds of sensors into this finger, right? The first sensor, for example, is this the strain sensor. It's just like a small wire which can be embedded into the skin, and when we touch some object using this hand, this strain stretches and gives us a signal that there was some like stretching of the finger. On the other hand, like there is like other conductive materials that can be used like for the for sensing some stretch. For example, this like conductive wire. other ways. So otherwise, we can put this liquid when we cast some materials, and some materials we can turn some materials into the sensors. So, for example, this liquid is conductive basically, and if we pour this liquid to some hydrogels, for example, it can work as a sensor. The hydrogels, like talking about hydrogels, hydrogels is like widely available. Like, for example, gelatin is also hydrogel. We can basically manufacture our recent research. We come up with this compound of the hydrogel that can be used as for self-healing and for sensing, and it is soft, and it can stay for a long time. And basically, we can manufacture this material this way, and we can just pour that material into the mold that we 3D printed, and we can use this material for some robotic applications, which you can actually also eat, and which is also biodegradable, which is the most important thing right now, like in the current age, when our like planet is degrading by our like our inefficiency in use of fossil fuels and other technology. Yeah, I will hand over to the final example when we actually cast it in this form, the gripper, using this like flexible biodegradable material based on hydrogels, and you will see the performance. Yeah.
Here's a demo of our printed sensorized glove. We print a kind of ionic hydrogel on all the fingers of the glove, and this kind of hydrogel, it has ionic conductivity, and its resistance, it depends on its width and length. If we bend our finger, the resistance of the hydrogel will change because of the length changes, and we can sense this kind of resistance to see the motion of our hand, and so that's how this works. And in addition, this kind of hydrogel can be printed on other surfaces to be used to sense other properties like humidity or temperature, which make it very easy to customize. So.
Cool. Hello. Hi, everyone. Welcome to the Observatory for Human-Machine Collaboration. My name is Ryman, and I will go through some of the examples we have here. First is the kitchen robots that we've been discussing about, and the biodegradable gripper. But first, let's go around and show you some of the example and back to this robots. So first of all, we have a musical robot, a robot that plays piano to simulate a piano player. And then we have a farming robot that can be placed in a lettuce farm and can harvest the proper already lettuce. And then the third robot here also we have a foodly robots. And this robot is picking and placing ready cooked food. And maybe one day, if you imagine, if you go to KFC, you might find one of these guys filling your pockets. So let's go back to our kitchen robots and then show you what is this robot about. So this robot is designed to mainly to prepare food and also figure out what is the taste of the food as well. So we have very simple probes here. They are conductive sensor, measure the currents between them. And with this probing the food in many times, we will know many information. What is the food taste like? What is the salinity? What is the humidity? And so on. There's more to that. But also thinking about that, how we can handle food and how we can cook it and so on. If we use just a normal sticks or whatever available in the kitchen, it might break or might melt and so on, especially with some robots here. Why not having biodegradable gripper that can be actually eaten? So it can be one in one plate. So let's try this experiment and see how we can do that. So we will try to have a strawberry picked. By the robots. We turn this chocolate contents. And then the robot will go and dip the strawberry in the chocolate. So it'll make it nice and tasty. And then the moment of truth is actually eating a groover. Thank you very much.
All right. Thank you, Roman. That's great to see. We're just coming to the end of our stream now. We've got a brief amount of time for some questions. So I'm going to add everyone back into the stream. Well, leave Roman to last to give him some time to finish eating. There we go. And we've got one question I'll put up on screen here, which is, could we use our robotic hands or the soft sensors for implants? And I think I'll pass that to Arsen. If you're happy to answer that, I'll unmute you there. And let's just hear your thoughts on that.
Can you repeat the question?
Yeah, it should be on your screen, but could we use the robotic hands or the soft sensors for implants, say, in the human body?
Oh, yeah. It's actually, it's a very, very good questions that we wanted to cover, actually. We know that, like, in prosthesis, for example, so we basically attach the artificial limb to the patient, and then basically patient doesn't really feel anything through this, like, artificial hand or artificial leg. And one of the priority research area is to really put the sensors into those prostheses and to convey this information to the human, so the human can feel it in a way it feels the original hand, like or in some signal that can be interpreted in the right way. So the user, for example, can feel that the object is like soft or hard, or for example, to feel some texture on top of the object, or some other things, like, or like feeling temperature, also very important when the user operates with some things in the kitchen, for example. Again, it's very very important and like priority research area right now in the bio-inspired robotics.
That's perfect. Thank you. And we'll leave our live stream at that. If you joined during the live stream, we're going to be back at 4:30, so you can catch some of that stuff that you missed. But otherwise, check out some of the other live streams that are running at the moment. And thanks for watching.
Thank you.
Hi everyone, welcome to Bio-Inspired Robotics Lab. Bio-inspired means that we inspired by the nature and by the biological organisms, which are very efficient. Like the bird flying like dozens of kilometers consumes the energy of just like a small amount of food, right? And the same as the running cheetah is like really fast, but consumes a limited amount of energy for that. And the key thing is that biological organisms are very flexible. They are soft. They perform like different tasks in the most efficient way. And we also in this lab trying to capture those important characteristics, but for the robotics world. For example, in this example, you can see the elephant nose is basically the end of the trunk which the elephant usually utilize for different kinds of tasks. For example, like elephant can pinch the objects like fruits and then obviously eat it later. It can suck the bigger objects that he cannot pinch, and also just like move and like pick and place or again consume it. It can wrap the object. Like for example, we can reproduce this with a stiff flop robot and so on. So it's like very efficient and very practical. And we are trying to use to make this gripper as practical as the elephant nose. We also do a lot of another important aspect is like that the biological world is like self-healing. It can recover after small or even large damages. For example, this material, like this finger, can recover itself after relatively big damage. Like what we need to do, we just need to leave this finger aside for for a limited amount of time, and it will self-heal, and we can reuse it, and the property will it will keep its original properties. We can manufacture it in a different size depending on the mold. And we also do in our lab a lot of studies human as the target biological body. Like for example, we study a lot of human hands because we perform a lot of tasks that robot cannot do yet, and we do it like quite nice, and we want to capture those characteristics of the human hand and to employ the robot with similar capabilities. So I will, the next presenter will be fun. He will actually show how this human hand performs the tasks with the capabilities of sensing and actuations. Yeah, please, Fan.
Here is a particular example of the robot hand that we're making. A normal robot hand has a lot of sections, and motors between the sections actuate the fingers to make it grasp the object. However, in our project, the robot hand is soft and without any actuator inside the hand. This is inspired by a natural discovery that the behavior of animals do not only result from their brains, but also result from the interaction between their body and the environment. So we build a passive soft robot hand, and it still successfully pick up the ball because of the stiffness of the fingers. But one question raises: how does the robot hand know where the ball is and whether it pick up the ball successfully or not? In fact, inspired by the human tactile sense, we build airbags inside the soft robot hand, and they act like soft sensors. When the hand contact the object, the pressure of the airbag will change, and this data will be collected by the robot, and then the robot understand whether it pick up the ball successfully or not, and try to improve its successful rate by changing its stiffness of the finger.
Okay, and we've just seen some examples there of why we might use soft sensors, because they replicate the kind of sensors we have in our hands, soft, flexible, bendy, all over our bodies and all over nature as well. But soft sensors are often much harder to work with and interpret the data from. So if you think of a classic non-soft sensor, a sensor that might be in a rigid robot, this is for sensing temperature and humidity, and it's fairly easy to get the data from. I just need to plug this into what I'm interested in, and then I can read one channel out for temperature, one channel out for humidity, and that's all I need to do. But if I take a soft sensor, something like this inflatable finger, which has soft sensors printed along the bottom to tell us how it's deformed, it's much harder to get that information because it might be deforming by bending, but it might also be deforming by twisting, by stretching, by a different combination of these. And we need to try and work out which one of these states it's in just from the information from this single sensor along the bottom. So sometimes we might do that by looking at where the actuator's been before, so what states it's been in, whether we know it started twisting at some point, and so it's more likely to be twisted now, or we might look at the information from a previous database of information that we've built up about how our sensor responds to lots of different deformations and deformation types. So that's what's going on down here. We've got a different sensor, which is a gelatin hydrogel based skin here, which can sense where it's pressed and how it's pressed, and even if it's damaged. And we're in the very early stages of collecting this information. We're building up just how it responds when it's pressed in different locations using a single robot arm, pressing it in places that we know about already. And then later on, when we don't have this robot arm here, when something else is pressing our skin, we can rely on this previous source of information to build up what and where our sensor is being pressed. And that's a real use of this material, which is also biodegradable, which is also edible, and is really easy to make. We make it up in our fabrication mezzanine, where Arsen is at the moment. So I'm going to hand back to Arsen, who can tell us about it.
Yeah, thank you, David. It was like a very good introduction to what actually we do and how we embed the sensors into the objects. But the details I will provide in this area. We actually the most of fabrications we do in this mezzanine floor. So we use two kinds of approaches. Like first is like a casting and molding approach, where we can have some materials like silicone or other type of rubber. We make a mold, and then we pour the components of the material, and then we cure it, and then we got the skin like flexible material. It's usually used in the soft robotics. And another kinds of is like print the hand or any other like a body part and robot part directly in the 3D printer using the soft materials. Either of methods are not perfect. Sometimes we have to decide either we go this approach or that approach. And in most cases, we even print some parts in 3D printer. Like for example, in this case, we printed the skeleton and we casted the skin. So basically, yeah, it's limited by our imagination only, and we can do basically much more. And how do we sense? David was showing you how he embedded sensors into this sort of finger, and the sensor actually looks like this. And you can, in the casting time, in the period when the material is getting cured, you can embed this sort of sensors which measure the strain. And if we embed it into the finger, when you apply some deformation, we will feel the strain signal, and we can figure out that okay, the finger is touching something. And also we are interested in self-healing materials, and we're interested in self-degradable and sustainable materials which we can even eat. One of these examples is this like hydrogel compound. It is similar as a gelatin, but it can stay for a longer time, and it has like sensing capabilities. What we can do, we can basically make this sort of material, and we can pour it into the mold which we made using like 3D printers, and we can make make a gripper out of it. But what we can do, we can also print the sensors and directly onto any type of surface. This will be introduced by the fan, and the gripper that we are making using this mold will be introduced later on by Raymond. Please, Fan, take over the stream.
Here is a demonstration of a sensorized globe that we make. We printed a kind of ionic hydrogel on all the fingers of the globe, and this kind of hydrogel has ionic conductivity, and its electronic resistance is very sensitive to its length and area. So when we bend this kind of globe, when we bend our fingers, the resistance of the hydrogel will change because its length changes. And we can detect the motion of our finger by detecting the resistance of this kind of hydrogel. And in addition, this kind of hydrogel can be printed on other surfaces and be used to sense other properties like humidity and temperature. So this makes it very easy to be customized. Now let's pass it to the OHMC.
Hi, everyone. Welcome to the Observatory for Human-Machine Collaboration. My name is Ryman. I'm going to take you a little bit, show you some of the examples in robotic that we have here. One of them is the kitchen robots that we're going to demonstrate later. But first, we're going to show a few other examples. And they are all interesting, of course. So the first one is a musician, basically, is a robot that plays piano and simulating piano player and matching the MIDI in both the simulation and real world. Another robot is a farmer. This robot can be placed in a lettuce farm and harvest the ready-to-harvest vegetables. And the other robot is Foodly. So this robot handle ready cooked food and package them so it's ready for customers. So maybe one day we will see one of these guys in KFC while you order and fill your food in the pockets. Cool. And we also have some tins for planting and automatically planting trees so we can track their growth and see which one is growing faster and so on. Let's back to the kitchen robot again. So this robot is basically trying to find, similar to a chef, where you're trying to, while you're cooking, taste the food and so on. So we have a sensor here, 2 props that can be propped on the food so many times. And these are conductive sensors, so we could measure the currents in between them. And with those, we could find a lot of information coming out from the dish that we cook, such as the salinity, humidity, and so on. And so if we want to handle the food, this is just for sensing, but what if we handle the food? We can't use just maybe the same normal things we use in the kitchen in case of any error with the robots. So we would have, or better option is to use the biodegradable grabber, right? So it can be part of the food. It's part of the dish that we have. So this is a biodegradable grabber made from gelatin, as it's been mentioned by my colleagues. And it can handle grabbing different type of objects. We'll just want to run this robot. So if we have this robot and have some objects in there, it can grab some of these objects, such as food, strawberries, and so on. And we have this chocolate fountain. So we just wanted to dip actual actuator in it, just to show you that this grabbers actually can be eaten. And thank you very much for joining us. Cheers. Bye.
Thank you, Roman. Looks delicious. So we're coming to the end of our stream now. We've just got time for some questions. So I'm going to throw everyone back up on screen so we can go through them. So we'll have Fan back, we'll have Arson back, and then Ryman back here. So hopefully you can all hear us. And I think the question we definitely want to know the answer to would be, how did it taste? However, it looks like we don't have Ryman there. So we might come back to that in a second. And instead we'll ask, how long has the hand been running? Which I think is a best question for Fan to answer. So Fan, do you want to tell us about that?
Yes, the hand can, one iteration of the hand running is about 10 seconds. And it can be run like 100 times, 1,000 times to just make it improve its performance and make it successfully pick up the ball. So indeed, in the presentation, indeed this hand is not successfully picking up the balls, but after maybe 1,000 times of training, it will successfully pick up the ball.
Perfect, thank you. And hopefully Ryman can hear us now. So if so, can
Yes,
you
I can hear you. Sorry.
Can you tell us how the actuator tasted?
Oh, that's a very good question. It's it's up to you how you can make it, how it tastes you want it, because you add all your own flavor. We flavored it with some gravy kind of flavor, so it's almost like it tastes like a lolly, but I don't think so. We are a good chef yet, so it doesn't taste that great yet. But we couldn't make it the way we wanted it, so it's all good with that. Don't worry about that. We still can make it a better flavor.
All right, interesting. Thank you. So that's the end of our live stream. We'll leave it there. If you've joined near the end, we're going to be back at 5 o'clock for a whole new live stream to start again. Feel free to flick around the others in the meantime. But yeah, thank you and bye.
Hello, everyone, and welcome back to Cambridge, to Bio-Inspired Robotics Lab. We do bio-inspired robotics. Bio-inspired robotics means that we're getting inspiration from the nature, from the biological organisms that are shaped through this like long process of the evolution. For example, like the birds, they are very efficient in flying. They can fly dozens of kilometers, relying upon a small amount of food. The cheetah is running very fast, again, relying upon a very small amount of food. One of other examples, like elephant trunk, it's multifunctional basically. The nose of the trunk, the elephant can pick up the fruit. The smaller fruit it picks by pinching. The bigger fruit it picks by suction. But the bigger things, the elephant actually lifts by the trunk itself. And we've got several questions about the trunk. Where is the trunk? You're talking about the trunk. So we brought up the trunk, and my colleague will introduce you an elephant trunk.
Right. Hiya. This is elephant trunk that I made today and yesterday. Well, basically is a series of pneumatic muscles connected together. So the way it works is that inside is actually a balloon, and outside it has like a mesh. So when you pressurize the balloon, it contracts. So therefore, it can change shape, like an actual elephant's trunk.
Yeah. So it's very exciting that like after a short period of time we will have a complete trunk, and maybe at some point we will have an elephant also in the room. Yeah. So we also do some other bio-inspired parts, like for example human hand, which will be introduced in details by Fen. Please, Fen, take over the stream.
Here is an example of robot hand that we are making. Sorry. Here is an example of robot hand that we are making. So when a normal robot hand has a rigid body and a lot of sections, the motor between sections will actuate the fingers to make it grasp the object. However, in our project, our robot hand is first soft, and second, it has second passive. That means it has no actuators inside the hand, but it still picks up the ball successfully. It's because this kind of robot hand is inspired by a natural discovery that the behavior of animals do not only result from their brains, but also result from their interaction between their body and the environment. So the passive soft robot hand successfully pick up the ball because of its stiffness of the finger. But here comes to another question: that how does the robot hand know where the ball is and whether it pick up the ball successfully or not? Inspired by human tactile sense, we built some airbags on the surface of the robot hand, and when the surface contact the object, the pressure of the airbag will change, and the data will be sent to the robot. Therefore, the robot will know whether it picked up the ball successfully or not, and then use this kind of knowledge to improve its successful rate by changing its stiffness.
Yeah, and that's an example of soft sensors and why we might want to use soft sensors, which can be bendy, which can be flexible, which can be stretchable. And that's much more like the kind of sensors we have in our hands, in our fingers, in our bodies, and that we see in nature. That's much more similar than, say, a rigid solid sensor we might plug into a normal robot. So something like this might be one of those sensors. It's rigid, we can just plug it into some electronics, and in this case, if we do that, it'll tell us the humidity and it'll tell us the temperature of our environment just by reading out some numbers on specific channels of this sensor. But soft sensors can be much trickier than this. So I've got a soft sensor here instead, which has been 3D printed along the bottom of this inflatable stretchy finger made of a hydrogel material. And this sensor is to tell us how deformed the finger is. But because it's soft, it might not necessarily just bend. It might also bend and twist. It might bend, twist, and stretch. And just from this sensor response, we have to try and work out which of these many, many states this finger is in. And there's a few ways we can try and solve that problem. We can look at the sensor response over time, so we can see that it starts to twist, and so we know that later on it's going to be in a twisted state, or the same with stretching or bending. Or we can look back at a memory we have of previous deformations where we've known exactly what state the finger's in and we've known the response. And if we've got a huge database like that, we can essentially predict which state the finger's in now. To build up that database is pretty tricky, but that's what's going on another example over here. We've got a sensory skin which is stretched across, made of that same material, and can sense when it's being pressed, when it's being deformed. We're in the early stages of training at the moment. It's just learning how it responds when it's pressed in lots of different locations by this robotic finger. And later down the line, that finger won't be there, but it'll draw back on its memory of this moment to know where it's being pressed by something else when it's on a robot. And yeah, that's one use of this material. This material is also edible, it's biodegradable, and it's really easy to make, which we do up in our fabrication mezzanine. That's where Arsene is at the moment, so I'm going to hand back to him.
Thanks, David, for introduction and highlighting the importance of the fabrication process. Actually, fabrication is not that easy, and we are doing fabrication is basically in this area. We have two types of fabrication. The first type of fabrication is like by printing, by 3D printing. Like these days, we have like a wide range of materials, like from the rigid ones, like a plastic, for example. This I can we can like basically print like the molds and cast some things on it, or it can be like flexible, but it has its own limitations. Like in most cases, we also use the molding and casting the silicone or some other sorts of rubber in 3D printed casts, for example. And then in most cases, we need to have the combined approach. Like for example, in this case, we have a rigid skeleton implanted into the silicone-based flesh and skin. The important thing about the sensors that David was mentioning, like there is a wide range of different sensors, but the main idea is to during the fabrication process to put this sort of strings into the skin of the robot. So when we can touch it or bend it, it can sense the strain signals and use it for some more complicated tasks, like Fan introduced the ball picking task or any other tasks. Sometimes we can make any material being a sensor, so that in this case, during fabrication, we can put some chemicals, making those material sensitive for strain or for compression. Well, the material that we will be using in this in our demonstration scenario is hydrogel. It's like a gelatin. You can basically eat it, but by adding some material, some conductive material like salt, it can have ionic conductivity and it can be used as a sensor. Basically, when we have this kind of compounds, we can heat it up a little bit and we can mold it in this 3D printed shape. So we can have, for example, gripper, which will be used at the end of this demonstration by Ryman. But also another important thing, like using this material, we can basically print it on top of any sensor, any surface, and use any object. We basically sensorize any object. And this demonstration case will be provided by Fan Yi. Fan, please take over the.
Here is a demo of our sensorized glove. We print a kind of hydrogel on all the fingers of the glove. And this kind of hydrogel has ionic conductivity, and the electronic resistance of the hydrogel is very sensitive to the changes in their length and their area. So when we wear the glove and bend our finger, the resistance of the hydrogel will change because the length of the hydrogel changes. And in this way, we can sense the motion of our finger by sensing the resistance of the hydrogels on the glove. And in addition, this kind of hydrogel can be printed on other surfaces and used to sense other properties like humidity and temperature, which makes it very easy to customize. And then let's pass the turn to the OHMC.
Welcome to the Conservatory for Human-Machine Collaboration. My name is Ryman, and I'm going to show you some of the examples we have down here. Well, we have the kitchen robot first. We will come back to this guy. But first, we're just going to show you a little bit in a 360 degrees. So one of the first one is a musician robot, which a robot that plays piano and basically kind of simulating a piano player with the soft fingers that some of the example you show upstairs. Another robot is a farming robot. This robot can be placed in a farm and can harvest lettuce, ready lettuce, so it can be ready to the market, from the robot to the market. And then the other robot is the foodly robot. So this robot is handling ready-made food and basically packaging them to the customer. So maybe one day you'll see one of these guys in a supermarket or in a food industry. Cool. And also we have some of the tins for observing and monitoring automatically how the plant's growing and so on. So let's go back again where we started, where the kitchen robot is. So this is a kitchen robot. The robot has almost like a taste sensor. So this is conductive probes that they can measure the current in between them. And this can be put or placed on food, on top of food many, many times when the robot is cooking. So we could know what does the food taste like. For example, salinity measure, we could see the humidity and so on. So all these sort of measurement that we need from the food to understand how it tastes like. Well, also when the robot cooking food, we needed something, the gripper should be something more biodegradable, for instance, or not damaged from heat or so on. So we wanted something that matched the way that we could work with food. And that's where the gelatin gripper, and it's similar to what my colleague explained earlier, we have these gelatins gripper that can be gripped to different foods and then can be eaten after. So let's show you something like what the robots would do and run this quickly. So if this is a gripper on the robot, if there's any object here that can grab it, food or vegetables or fruits or anything like that. And what we're demonstrating here really is just dipping the gripper in a chocolate fountain. And so it can be maybe more delicious. So what we can do is actually eat in it. So here we go. Delicious, dipped with chocolate, and can be eatable. Thank you very much for listening and really, really for your question. Thanks a lot.
Okay, thank you, Rowan. So, like you said, we do have time for some questions. So what I'm going to do is I'm going to bring everyone back on screen. So let's have Van back, let's have Arsen, and then as he finishes eating that bit of gripper, let's have Ryman as well. Okay, so we've got some questions here. I think the first one, I guess, is to be sent up to Arsen and is about our robotic trunk, which is when will the whole robotic trunk be edible?
Yeah, yeah. Actually, we saw these questions, and yeah, our colleague came to this. We're actually working on the trunk currently, and it will be activated by pneumatic muscles. So basically, we can bring them together to the part which we already mastered. It's like working, and it's actually a good prototype right now, and we will bring them together, and we will try to make a very flexible and very strong gripper out of these two components.
Yeah, thank you very much. And then we've, I think, had this question before, but it's the one we definitely want to know the answer to. And that is, how did the gripper taste? Roman, I don't know if your thoughts have changed since we last asked this, but we'll ask again.
So the robot, the robot tastes the way you like it tastes, basically. We mix it here with some fruits flavor. So it's a gelatin. You mix it whatever flavor you wanted. So almost like a lolly, basically, literally like a lolly in the supermarket. You want it sour and sweet and so on. But I think it tastes a little bit sweet because it's like a little bit fruity, dip it with with chocolate. So it tastes chocolatey, I would say, but you could do it the way you like, basically. Cheese, thanks.
Interesting, thank you. So that brings us to the end of our live stream. We will be back again at 5:30 for our final one of the day if you've missed anything else. Thanks for watching and goodbye.
everyone, and welcome back to Cambridge to Bio-Inspired Robotics Lab. Bio-inspired means that we are inspired by the nature, by the organisms, by the living animals, by human and all. Why we are inspired by biological organisms? Because they are very flexible, they are efficient, they are soft, and they can use the capabilities of their matter, like that they are soft, to do some specific tasks. And they are very efficient. For example, the bird can fly dozens of kilometers relying upon like a limited amount of energy of the food that it eats. Like the cheetah runs very fast and very long distance, just relying on the small piece of food it eats. And the robots right now are not as efficient, and robots are not as capable of doing some very fine manipulative tasks because the robots are rigid. And we are trying to bring this soft properties of the biological organisms to the robotic world, and that's what we are doing in this lab. One example is the robotic trunk, the elephant trunk. The nose of the trunk is actually very useful for the elephant, and it's like one of the most important body parts for the survival. It can pick up very small, tiny fruits by using the pinching of the nose, and it can pick up the bigger fruits and vegetables by using the suction mechanism. And it can basically lift very big things like using its muscles on the trunk. And that's what we are trying to bring to the robotic world and utilize it for the daily purposes. We also work on the human-inspired way, because the most of the things we used to do by hands are moving to the stage where robots are manipulating and doing things. But a certain task the robot cannot do, and we are trying to learn from the human how to do those complicated tasks. And we are trying to utilize the flexibility of the human hands in the robotic world. Like more examples will be provided by Fan. Please, if you could take over the stream and explain the human hand inspired applications.
Here is an example of a robot hand that we are making. A normal robot hand is rigid and has a lot of sections, and the motor between the sections will actuate the fingers of the hand and make it grasp the object. However, in our project, we make a soft robot hand without any actuators. That means on the hand, there's no actuator inside, but it still successfully pick up the balls. Why this happened is because we built this hand inspired by a natural discovery that the behavior of animals do not only result from their brains, but also result from their interaction between their body and the environment. So this kind of passive, soft robot hand can pick up the ball due to its stiffness of the finger. And another question raises that can this robot know where the ball is and whether it picks up the ball successfully or not? Indeed, inspired by human tactile sensing, we built some airbags on the surface of the soft robot hand, and when the hand contacts the object, the pressure of the airbag changes, and the data will be transferred to the robot. Then this robot knows whether it picks up the ball successfully or not, and then it's continuously learn how to adjust its stiffness of the finger to pick up the ball to increase its successful rate.
Okay, thank you. And so we've just seen there some examples of why we might want to use soft sensors in robotics. So soft, bendy, flexible, stretchy sensors. And they're quite different from the sensors we'd normally put in a robot, which might be something like this. So this is a temperature and humidity sensor. It's not bendy or stretchy at all. But all I need to do is just plug it in to the right bit of electronics, and then I can start to read out from 2 different channels what the temperature is right here and what the humidity is right there as well. And that's pretty easy. But if we take a soft sensor, and in this case, these are some soft sensors 3D printed on the bottom of an inflatable soft finger, they're much more like what we get in nature, in our bodies, the kind of tactile sensors that cover our hands and we find everywhere, and might be a bit more biological. But the sensory response that we get for these are much harder to interpret. And that's because to know the deformation of this finger, it might not just be bending, it might also be bending and twisting, it might be bending, twisting, and stretching. And just from this one sensor signal, we need to try and work out the exact position that this is in. And there's a few ways we can try and do that. We can look at the previous time series response of the sensor, which means look at how it's built up to the state it's currently in. Can we look at a point and say, it started twisting here, so we know it must be twisted now? Or the same with bending or with stretching, to try and work out where we are. The alternative is that we build up a really big memory bank of exactly how the sensor responds in a whole load of different deformation scenarios. So we bend it to the exact angle that we want and then measure the sensor response, and do that thousands and thousands of times so that we can look back at this set and know where our finger is. And that's the same reason that this robot around here is moving. We've got a sensorized gelatin hydrogel based skin here, which can detect, using some electrodes around the edge, where it's being touched, how it's being pressed, and even if it's being damaged as well. But to do that, we need to build up this database of known deformations. So we've got a robot arm here, which is just prodding it thousands and thousands of times in known locations at known depths. And at some point in the future, it will look back at this time when it doesn't have the robot arm anymore, and it'll know how it's being pressed by some external force. And that's really useful. We can use this skin not only to sense stuff, but we can use it for its material properties, because this hydrogel, it's edible, it's biodegradable, it's very stretchy, and it's really easy to make, which we do up in our fabrication mezzanine, which is where Arsen is at the moment. So I'm going to hand back to you, Arsen.
Yeah, thanks, David, for the introduction of the and highlighting some importance about the fabrication process of the soft robots. Basically, we use 2 kinds of the fabrication processes. The first process is just use 3D printer, right? We have various kinds of materials right now, like from the rigid PLA and ABS plastics that they are used like everywhere, to the more flexible materials like printed in this case. But still, like even though it's like flexible enough for certain applications, for the other more complicated applications, it's like not doesn't have enough properties that can serve for the longer period of time, or to be flexible enough for certain tasks. For these purposes, we are using the casting process. Like when we have like 2 components of material, we mix them together and then we cure and get rubber-like materials, for example, the silicone or some other type of rubber. And in this case, we can make a hand, for example, very close to the properties of the human flesh. And then another important thing is that we are not limited to use either this or that technique. What we can do, we can combine them. For example, in this case, we 3D printed the skeleton out of the like hard plastic, and we used the silicone to cast the flesh of the skin, and we can basically have the passive properties of the human hand in this case. Also, the sensors, like that David said, they can be different, but most of the time they are changing their voltage level when we stretch them, so they kind of sense the strain. And during fabrication process, we embed this kind of sensors into the say gripper or robotic hand, like And then when the deformation happens, we sense those signals, and then we use some machine learning algorithms to figure out what's really going on. It's like twisted, it's bending, or it's like stretching, or it's like twisting, bending, and stretching, as David just mentioned. And then another important thing is that basically we can turn any surface into the sensor. We can basically like 3D print and apply a thin layer of, like, say, stripes using some conductive material, like, for example, this hydrogel based material. And and then this will be like introduced by Fan in a minute. And it can be basically print to anything in your cloth, and then it can measure the amount of deformation of your cloth, or it can figure out if you're bending or if you're doing some certain tasks. It's good for the human-computer interaction, for example. And on the other hand, like, we can use the casting, and we can basically make the out of this material gripper, for example, and it will be it can sense the deformation. On the other hand, these kind of materials are biodegradable, and they are very good for sustainability. And furthermore, we can eat them. And it's like a highlight of this talk today. At the end of this talk, you will see how Raymond will actually eat the material prepared by from this using this material in this cast. I will give a speech right now to Fan. Fan, can you take over?
Hi. Here is a demonstration of a sensorized printed globe. And we printed a kind of ionic hydrogel on all the fingers of the globe. And this kind of hydrogel has ionic conductivity, and the electronical resistance is very sensitive to its changes in their length and area. So when we wear the globe and bend our fingers, the resistance of the hydrogel changes as their length changes. And then by sensing the resistance of these hydrogels, we can sense the movement of our fingers. And in addition, this kind of hydrogel can be printed on other surfaces to sense other properties like humidity or temperature. And this make it very customized, very easy to customize. Then let's turn to the OHMC.
Cool. Thank you very much, everyone, and thanks for all the information. And hi, we are in the Conservatory for Human-Machine Collaboration. My name is Ryman, and I'm going to show you some of the examples what we have down here. So this is what you see is the kitchen robots. We're starting here. We'll come back to it. I'm just going to show you around here what we have in the other corner, which is another interesting project, is the piano playing robots, which is thinking of it as a musician. And that's just to simulate how a piano player playing on a piano by getting the MIDI right. And then the second robots we have is a farmer robots. This robots can be placed in a lettuce farm and can harvest the ready lettuce, so they can be shipped directly to the supermarkets. And then the third one is the Foodly robots. This robot can handle ready cooked food and package it for consumers. So maybe one day you will see one of these guys in the supermarkets or the restaurants, so they can really package your food in there. And so also we have these tins that automatically handling the growth of plants and see which one is growing faster and so on. Cool, let's go back again to the kitchen robots and talk a little bit about it. So this robot has a sensor here. This sensor can be probed on food. It has two conductive probes and measure the currents in between them. So this robots can handle or prepare food and then measure with this conductor sensors many times in many places. And from this information, we will learn how the food tastes. What is it? Is it salty? What's the humidity like? And all this information that we needed from food before be ready for us to eat it. But also on the other side of the robot is the grubber. So if we handle food, we will also think about what type of tools we could use with this robot. Do we use the normal kitchen tools that we have? Or might be difficult to use it with the robots because it might be break or any error that could happen with the robots. So what my colleagues explain upstairs is about this biodegradable materials, hydrogel, specifically gelatin. It can be eatable. So it doesn't matter if it melts on the food or it grips it. Basically, it's good to go and it's good. We can eat it. So let's do this. Let's run the robots and show you this little experiment. So if we have this grubber, and if we have any object here, just like fruits or vegetable and so on, and can go and dip it in the for cooking. But here, we basically dip it in a chocolate. So why? To make it a little bit more delicious, so I can demonstrate and eat it directly. I forgot to say bon appetit first, but here we go. It tastes chocolatey and fruity as well. So thank you very much, and ready for your question. Thanks a lot.
Okay, thank you, Ryman. Looks delicious. So that brings us near the end of our final live stream. We've got just a bit of time for some questions. So what I'm going to do is I'm going to bring everyone back on screen. We'll have Van back on screen. We'll have Arsen back on screen. And then hopefully he's just had time to finish his gripper. We've got Ryman back on screen as well. So a question that came through during that from Claire, if I put it up, there we go, is what do you wish you'd known when you first started this project? Now, I think this came through when we were talking about the sensors, the sensorized hands, the sensorized grippers. So I might take this question and say that it's always about where we put the sensors is the difficult bit to know. We still struggle with that now. Do we just cover something in sensors and maybe be very inefficient? Or do we place the sensors a bit more tactically so we've got fewer to work with and be confused by, but we have to get the perfect position, which is still a very difficult question to answer. So thank you, Claire, for that. I've got some other questions here. I think this one must be down in OHMC for Ryman, which is how does a robot learn to play the piano?
The robot's basic, it's a very good question. Thank you very much for that. Matching, we're trying to do the simulation first in an environment to see how we could get the robots play and how can we match it with a real piano player. And something called MIDI that comes the tunes out of the piano. And that's how we can match what we can get from the simulation and then put it in the real robot. So we could feedback the loop from what we learned from the simulation, apply it to the robots playing with the soft finger pressing on the piano. This is one of the approach. It's still an ongoing research, and we really wanted to achieve that in a later stage, because we do build the hands, we do have the passive hands as well, and we wanted to collaborate that with how we can, the contacts between these hands, the passive hands, and the key of the pianos, how they press it, how fast, with the velocity, and so on. So we are working on that, and hopefully in a later stage we could demonstrate a robot that have a really nice piece of playing piano. Thanks.
Okay, thank you, Roman. Then I think our final question before the end is just here, and that applies to a lot of things that we've said around the place. We do a lot of 3D printing, but how many 3D printers do you have? I think, Arsen, maybe you're in the best place to answer this. So, do you know?
Yeah, actually, yeah. Thank you, David. We actually have like quite many 3D printers, like in different areas. We are using for the quick prototyping, we are using cheap 3D printers, like they are like all over the lab, and we are using like more sophisticated like printers that can be seen in the other corner of the lab, that we are using basically for making casts and for the long prints and the bigger volume. We have like more expensive 3D printer like located in the other building where we can print the material that changes the property. Like it can be like soft, or it can be hard, or it can transit like from the soft to hard, or it can be like multi-component. So we basically can print the hand in one print. Yeah, and then we have the modified printers, like 3D printer that you saw with the David, that we can put the gelatin and we can print on layers of sensor on top of any surface, or we can just even print the gripper, for example, from the ground. Yes, I hope this answers your question.
Yeah, definitely. Thank you, Arsen. That ties in nicely with my camera turning black for no real reason, but it's a good place to end the stream there. Thank you all for watching, and yeah, goodbye.